Good morning. Welcome everybody to our machine learning seminar. Today we'll have a pleasure to have a presentation from Professor Rolf Krause, who is a chair of advanced scientific computing in the Faculty of Informatics, and he's at the same time a director of the Institute of Computational Science at the Università della Svizzera Italiana. Rolf, the topic of the presentation is already present on the screen. So let me give the floor to you and please go ahead with your presentation.
Thanks a lot for presentation and for invitation. And today I would like to talk about training neural networks using multi-level and domain decomposition strategies. And multi-level and domain decomposition originally come from solving PDEs, elliptic PDEs, which gives rise to large symmetric positive definite sparse systems, but they are more versatile. They can also be used for optimization problems. And I would like to discuss a little bit how these strategies can be used for training neural networks. What I'm going to talk about, of course, is joint work. So my collaborators you see here. There's Alena, who is now with Karniadakis in Brown. Samuel is a PhD student, and Hardik and Ken are postdocs in my group. I would like to start with a little bit of a general argument, because I would like to comment later on approximation properties of neural networks. And if you look at what we call classical or model-based simulation, you might have an application. This could be computational mechanics, fluid mechanics, molecular dynamics, cardiac simulation. We do a lot in medicine. So what you do is you write down a mathematical model, and this is usually based on first principles. And energy needs to be minimized. You have an equation for movement. You have Newton's law. You have balance laws, conservation of momentum, whatsoever. So you have these mathematical model, and usually we do this in infinite dimensional spaces, Sobolev spaces. And then we prove there is a solution, it exists, and we discretize. We use finite elements, finite differences, finite volumes. And then the discrete model gives usually rise to a linear system. I mean, sometimes if you go for time-dependent problems, you do everything explicitly, but you get some linear or nonlinear system in a finite dimensional subspace. You have to choose maybe certain coefficients for your approximation, and then in the very end you get some result and visualize. Why I put this when talking about machine learning is a very simple argument, because what we do is we have a model, we approximate the solution of this model, and then we compute a solution of our discrete approximation. And the advantage is that somehow the approximation process itself and the solution process are separated. So you choose a usually linear subspace, you look for a best approximating element here, and then you compute it. Those are two different steps. This is something a neural network doesn't do. A neural network is mixing everything together, approximation and solution and whatsoever. And so we have less control. And this I would like to keep you in mind. And I would also like to keep you in mind that the approximation spaces usually we construct when doing finite elements are linear subspaces. You construct a sequence of increasing subspaces, linear subspaces. And in each of these subspaces, which might depend on your discretization parameter, you look for a best approximation. And this is a technical point, but very interesting. In your subspaces, you have a prescribed basis. You use piecewise linear finite elements, piecewise quadratic, whatsoever. You use a basis to approximate whatever you have, which means you have a direct connection between the coefficients in the development of your discrete solution and the approximating function you would like to represent, and networks don't do you this favor. So machine learning is slightly different. You don't try to understand what you do. I'm a little bit maybe unpolite at this point, but the argument is you have a lot of data and you have no idea on the underlying physics, biology, chemistry, whatsoever. So there's no first principles at all. And then you put your neural network. Now, these neural networks are very interesting beasts, because they don't provide classical linear approximation, but basically the approximating function you generate by training comes from unions of finite dimensional subspaces. So they are extremely rich. And what you can show, for example, is that with neural networks, you can approximate up to arbitrary position in certain norms, any function in certain Sobolev spaces. So you know they are sufficiently rich to approximate whatever you wish. What you do not exactly know is how they do it exactly. Yeah, because when you train your network, you do not know which approximation you get because we don't have control on this. So here you do training of the network. What does it mean? You choose somehow a basis in which you would like to approximate your unknown function, and you choose the corresponding coefficients. And then you hope that your network magically has learned physics, biology, chemistry, whatever was the underlying problem. So you do, while you do the training, approximation and solution simultaneously. And this means you do not know exactly what is happening. And in general, for most modern networks, you have a heavy overparameterization. Yeah, if you do polynomial approximation, or if you do a piecewise linear representation maybe of a function, what you know is if you change a single coefficient, then this will have impact on your solution at a particular point. Yeah, if you simply look at this piecewise linear function and you decide to change the value here, what is going to happen? It's going to look like this. Yeah, so if you change a single parameter, you know exactly what is going to happen in the function you approximate. For networks, this is completely unclear because the mapping between the weights you have and the eventual approximated function can even be unstable. There's a second problem, and this I just would like to put here because it's interesting in this discussion. And this is, you can ask the question, if you would like to train a network which provides on the unit cube an approximating function to your data with given uniform accuracy, yeah, so bounded error in infinity norm, how many samples do you need? Yeah, what people usually do is they have their data and proofs are done on the unit cube, yeah, because you're in each feature, in each component, you simply scale your data and then you approximate an unknown function on the unit cube. So you can ask yourself, okay, how many samples do I need to take in order to approximate a given function on the unit cube such that the error in the infinity norm is bounded uniformly, it's infinity norm on the whole unit cube? And the answer is, in practice, it's not possible because the minimal number of training samples for this task scales exponentially both in depth and input dimension of the network architecture. And this is quite clear because if you look at high dimensional approximation, or if you look at this simple 1D example, if you have your training points here and have no training points in between, then your network can do in between whatever it wishes. What we hope somehow magically is that during the training process, the network prefers this kind of regression here, but we do not know. So what we know is we can approximate anything with neural networks. We also know this approximation is unstable, and we know if we would like to have bounded error on the whole unit cube, we need too many samples. And this is a very well-known effect. Maybe this you know, yeah, how to fool a neural network. Because if you give strange input to a neural network, this is for classification. An example, that's a paper from 2015, also quite famous. If you give strange input to a neural network, it simply will classify with high confidence wrongly. Yeah, so this is what the network sees as a robin, and this is what the network sees as a bubble. This is what the network sees as an electric guitar. Remote control, I understand a little bit. Yeah, these might be the buttons in your remote control, but this is all input data you give to your neural network, and it will classify wrongly. Yeah, and this is interesting for adversarial attack because it means if I would like to get the data on your iPhone because it's using face recognition or by fingerprint, I will maybe not start to look like you, but I will simply provide noisy input and hope for a completely wrong classification of the underlying neural network. Okay. And what do we believe? And this is what I said by regression, what we believe is happening during training. I mean, it's all in high dimensions here. I did it only in 1D. If this is somehow the data you have, and a ReLU network, if you take ReLU as activation function, does piecewise linear approximation, then maybe that's your start solution. And then you hope that during training, you somehow get a better approximation to your data. This can happen. You can get something different, maybe because training data are missing here and here. You will run into bad generalization. What also can happen is that you only capture the noise, depending on architecture and your data. And what also can happen is if you really drive your loss functionality zero, that you run into overfitting, so you approximate your noise. Usually it says in the literature, overfitting is bad for generalization. And this can be, but doesn't have to be. Of course, if you find a nice regression, or if you do nice regression, somehow in the expectation of your data, you will get good generalization. But if you do overfitting with a highly overparameterized network, you can also get very good generalization simply because the noise is possibly evenly distributed. And now, whether you look at the error between this highly oscillatory approximation or this more smooth one, in practice, it doesn't really make a difference. So it's very subtle what we do during training, because we construct our approximating function, we decide on its smoothness, and we decide on the approximation error. And what people do in practice, they use, for minimizing the loss function, which is basically only error on a certain subset of your data, they use very, very simple functions like gradient methods, first order functions. Problem is your energy landscape is usually very rough, which is also an indicator for the simple fact that if you're looking at this one here, what does it mean you have a rough energy landscape, right? Because it's the change of energy when you do a little bit of variation in the weights. And if you have an energy landscape like this can be an indicator for an instability in the mapping between weights and final approximating function. Yeah? You choose, you move a little bit on the weights, and you get a completely different approximation quality, yeah, because loss goes down, goes up, whatsoever. So the mapping between the weights and the actual networks shows some instability. And we hope that during training somehow we arrive in a deep and smooth crater which will not show this behavior, but we do not exactly know. So training, from my understanding at least, has many functions. You're looking for a good approximating function. You're looking for a solution which is stable in the sense that small perturbations in the weights do not perturb too much your eventual approximation. That's also part of the training. And of course, you would like to deal with very large data sets. Okay, so what we know is that size and complexity of data set heavily influence training. And we also know that gradient method, even if you add momentum, yeah, it still remains a first order method, and momentum is a little bit like Krylov acceleration, which is a technique we already know from the 60s. Even if you use these modern techniques, it remains a very slow method for minimizing functions. What the advantage is for gradient-based methods is you can prove global convergence if you fulfill some conditions on your step and on your step size. But in principle, for gradient methods, you can do some convergence proofs, and you can generalize those also to stochastic gradient. Okay, so training is difficult. We know that we can approximate any function. So what they say is networks are quite expressive. What we do not know is which function we get after training. Yeah, so whenever they tell you in machine learning, I can approximate any function, the correct answer is I know, but you have no idea whether the network you have trained is by any means related to the function showing up in the proof, which in principle could approximate your sort classifier or whatever you are interested in. Okay, so we do not know whether the network we have trained actually is some best approximation. Size of the network architecture is important for approximation qualities. And what we also know is that standard training methods, this is what we also know from PDEs, tend to ignore high frequency information in the data. This is what people call spectral bias. And we need to initialize our weights properly. And in practical terms, if you would like to train your network well, and this is very important, you have a very, very costly hyperparameter search. So you do many training runs, each take a lot of time and will cost a lot of energy until you get a reasonable solution. Methods are not parallel. You have to choose the parameters. And as I said, mapping from weight space to approximation function is not necessarily continuous, and even you can prove, and this is also a result I very much like, that networks which are close as approximating elements in function space in general do not have close weights. Yeah, so that's some kind of inverse instability. You take two functions which are very close and look at their representation by means of networks. And this representation in weight space is not necessarily close. Yeah, so this tells you these networks are very difficult beasts, and there's not a direct connection between the weights and the approximating function, which is completely different for classical interpolation and approximation. If you have an interpolation polynomial and you have the coefficients, you have everything under control. You know what is happening if you move every coefficient. For a network, you don't. Okay, so I would like to talk shortly about how to improve efficiency. And the underlying idea is quite simple. There's two ideas. And the first is to do a multi-level approach. So you have, here I put a mesh, but you have in principle a problem with many, many unknowns. You take a problem with less unknowns and then even one with lesser unknowns, and somehow you hope these will build a hierarchy of approximating functions, maybe some kind of frequency decomposition, or in the networks language, you can call this somehow low level, mid level, and high level features. And then you would like to train your network by using information on these different levels. For elliptic problems, we know this can be quite efficient. We know that multi-level decompositions, which basically are using decompositions or scale decomposition like this, form approximate orthogonal basis of our solution spaces and so give rise to optimal preconditioners. For networks, we believe this idea might be usable, but we don't have this well built theory as we do have for the elliptic case. The second possibility we have basically is we can go for parallel minimization. And what does it mean? We take our large scale problem, we divide it into nonlinear, usually sub-problems. Then we solve these in parallel, we recombine everything, and we get our updated new network. So that's the two possibilities we have. And of course, if you wish, you can combine both. You can do a multi-level method in parallel, or you can do this domain decomposition. Or what you also know from PDEs, if you do domain decomposition, you need a core space in order to improve a little bit convergence. Okay, and now I just would like to give 2 or 3 examples, so then that we can have a discussion, because from what I understand, I can give something like 10 minutes examples now, and then we are going to discuss in terms of timing. And I would like to talk first about decomposing a fully connected network using domain decomposition methods. What we did here is we have been trying a network to approximate solutions of partial differential equations, which is interesting because we know exactly about the structure of the solution. We know the solution, and so we can very easily have a look at the properties of the network. So we approximate our PDE here. It's going to be a time-dependent PDE. We are going to have initial conditions, we have boundary conditions, and some linear or nonlinear differential operator, and we would like to approximate the solution on our space-time cylinder by means of a neural network. So we would like to approximate the solution. Here, this is our U, using a neural network on this D+1 dimensional space-time cylinder. Okay, loss functional is quite clear. You take the residual of your PDE. You take error in boundary conditions. You take error in initial conditions. You could think about taking different norm than Euclidean norm here, but that's what we do. So you approximate your operator, your boundary values, and your initial conditions. And then you can look at the error between the approximation provided by the neural network and the function you know is a solution of this PDE. Then your network will provide some solution, which is here this one, for a, let's say, fixed finite element of finite difference space you choose. You know or would know in principle about the discretization error. So you could do the following triangle inequality. You can say you can estimate the error of the network by looking at a comparable finite element discretization at the error of this one, then looking at the error between the optimal approximation you can get for your architecture and the finite element approximation, and eventually the error you make during training. As I said, we don't have those because it's a non-convex minimization problem, so it's very difficult to get the optimal solution, but at least we can get an idea on how to understand a little bit what is going on during training. Okay, so the discretization error itself, of course, is determined by the number of collocation points, and the network approximation error is determined by the network architecture, and the optimization error somehow is determined by the choice of the optimizer, but also, of course, keep in mind that we in practice cannot separate between these two. What do we do? And this is just in order to motivate a little bit our domain decomposition strategy. As you know, if you would like to minimize a function, you can also look at the necessary first order condition. Yeah, you look at zeros of the gradient of your objective. And if you look at the gradient of your objective, here we are. Necessary condition for a minimizer is to have this zero. And this is simply a nonlinear system of equations in your weights. And weights are here called theta. What we do is we take our nonlinear function and we do some right preconditioning. So we construct an approximate inverse function g, which is somehow acting on the weights. And then we try to minimize this function h because we believe it's easier to minimize h than the original f. And this g is constructed locally. And how do we do this locally? We simply do the following. We take the network and we cut it, in this particular case, between layers. Yeah, so this is entrance layer, first hidden layer, second hidden layer, third hidden layer. So we cut between layers and block the corresponding weights. Then what you simply do is you can have a restriction operator which is selecting the corresponding weights. You take the transpose, so you can extend whatever you have changed here to the whole networks. So what we do is we take the set of all weights. We select a certain subset, this one here. We do something on this subset, some local training, and then we add the resulting correction to the global network. Localizing local solution extension. And this corresponds basically to minimizing our loss functional with respect to a blocked loss functional where the variables are nothing else than the weights on your corresponding subsets. And what we do is a little bit tricky because you get the corrections on these subsets. You have to sum them all up. You have to choose a step size. And then after computing on the local corrections, you need to take care of the global correction step. If you think simply in terms of a minimization problem, right? If you minimize on parts of your variables, then after having solved the local minimization problems, you need to take care of connection between these different subdomains. And this is what we do in a global post-processing step. Yeah, so you have a company, you have 5 employees, everybody is doing something, and then they need to meet in order to synchronize whatever they have been doing locally. This is done by some variant of BFGS. So we use approximation of second order information. Please keep in mind that BFGS a little bit, at least for convex, what you know for convex problems, it behaves like CG. So it's a function which ignores a little bit, or which let me put it like this, which smoothes a little bit second order information. So it's not too bad to use it here. And I just would like to show you some examples. We did different types of PDEs, but since we don't have so much time, let me just show you the following result. What you see here is loss with respect to different decompositions. So the question is, if I decompose my weights into smaller subproblems or more smaller subproblems, how does it affect the training speed? And we had a network with in total 6 layers, and we decomposed into 2 subproblems, so 3 layers each, 3 subproblems, 2 layers each subproblem, or each layer is a separate subproblem. And if you look at the loss, this is red is 2, blue is 3, and this violet is 6. You get better convergence if you have more layers in this particular case. This is also interesting because this means if you parallelize, because it's a nonlinear process, if you parallelize, you cannot expect to get the same solution as you get for the one processor variant of your minimization process. It's a different algorithm, which depends on the number of cores you run, and you would like to understand how does it depend on the number of cores. Let me put this differently in terms of, how can I say, optimization language. If you do a gradient step, you replace your objective by a linear model. If you do a Newton step, you replace your objective by a quadratic model. If you do a parallel solution, as we do here, you do replace your objective, if you use locally second order models, for example, by 2 quadratic models or 3 quadratic models or 6 quadratic models. Right? Because each of these subproblems will induce one linear or quadratic model, depending on what you do on this subdomain. And so this is at least my belief. That's the reason why you get better results, because 6 quadratic models can better approximate a strange loss function than a single quadratic model. But this is just a little bit in order to understand heuristics. So it helps to do this kind of parallelization, and this is, we believe, advantages if you go for large-scale problems. And what you see here is ADAM, which is somehow momentum method, right, which is state-of-the-art for large networks. Here you see relative error of the result, and here you see ADAM, and here you see different variants of our parallel training method. That's an additive one, that's a multiplicative one, and this is one with approximate second order information. And you can see that depending on the PDE and the particular type of the PDE, I'm sorry, this is not our parallel method, this is just BFGS, so approximative second order information on the whole problem. So this, if you look here, this is ADAM, first order plus momentum. This is a global approximate second order information. And this is local approximate second order information plus decomposition. Okay, and yeah, as you can see, decomposition pays off. And the beauty is you do not have to tune so many parameters. Okay, and then I just would like to go for the last 2 minutes, which I do not have anymore, but I would like to do it nevertheless. I would very like to shortly comment on the multi-level approach. There's a huge literature on doing multi-level methods for minimization problems, convex, non-convex. There's full approximation scheme, there's MGOpt, there's monotone multigrid, there's recursive multi-level trust regions. So there's a lot of methods available. We did recursive multi-level trust region for non-convex minimization and monotone multigrid in particular, also in mechanics. And what you do is you do some minimization on a fine level, you go to a causal level, minimize, even causal level, minimize, you sum up all the corrections. And if you do this in a network, there's two possibilities to basically construct your multi-level hierarchy. And the first possibility is to coarsen in data. Yeah, that's very simple. So what do? You just create a hierarchy of data sets by coarsening, and then you create your coarse level models with the corresponding loss simply by looking at coarser data sets. But the parameters of your weights somehow, at least in space, for this particular example, remain the same. And the second possibility, let me just show how this works. So this already can improve convergence significantly. And here you again see standard optimizers against multi-level variants. And as you can see, the multi-level variant is not always better, the data coarsening, than maybe a standard training method, but it seems to be more robust with respect to ill conditioning difficulties in the data set. Yeah, this is also clear from the theory of PDEs, because, you know, multigrid is an optimal preconditioner for problems which are related, if you wish, to a certain metric. And this very good preconditioning property seems to translate here. The second, and this I only would like to tell you for race nets, we have been trying for building up a multi-level hierarchy in the weights. If you look at the RaceNet architecture, RaceNet is a little bit like an iterative solver. You get your new weights by taking your old weights and reducing somehow the error you would like, or you get from looking at your loss function. And this you do in each block again and again. So you have an initial iterate, you make a correction step, you get a beta iterate, make a correction step, and so on. What you can do, you can nicely interpret, you can nicely interpret this structure, if you wish, as type of ODE. And then you can interpret somehow or let me put it differently, and then you can do the following. You can skip each second block in your RaceNet and just build a RaceNet which has in principle the same architecture, but for example, half of the blocks. This makes theoretically sense if you interpret this here as a discretization of an ODE. Yeah, this looks basically like explicit Euler, and if you put a step size in front of your F, this is going to be your update step in each time step, and this is just your discrete time evolution, and then you can interpret this here as a coarse time step, and you can interpret this as a fine time step. So if you wish, you can give it a theoretical background. And then you can simply say, okay, if you have trained your coarse network, then you can decide to update the networks of your original fine network by simply adding the corrections here, or by maybe distributing with some weights 1/2 and 1/2. And this also works very nicely. You need to add a global control convergence strategy. We are doing this using trust region methods. And as you can see here, if you look at standard training methods, and at our multi-level training methods, no, I'm sorry. If you look at this is how it has to be, because if you look at the standard training methods and if you look at our multi-level training methods, you get somehow to the same accuracy, but significantly earlier and with less steps. So there is many possibilities to transfer ideas we have from solving PDEs to training neural networks. You can do this in a multi-level fashion, in a domain decomposition fashion. You need to think about convergence control, which, as I said, we do using trust region. I didn't talk about this now. And we see in practice it works very well. We have a lack of theoretical understanding. Yeah, we have the theoretical understanding completely for elliptic PDEs. We have it partially for non-convex minimization, and it's very difficult for doing this for networks, because if you do, for example, coarsening in weight space, it's not clear how to define a coarse weight space, because it's not clear what the weights describe themselves. Yeah, this goes back to the original discussion, because in a finite element context, you know what your coefficients are. You can connect them to an approximating function. In the network context, that's not so directly possible, at least not on paper, or at least we do not know how to do. So there's still many questions open, and with that, I would like to thank you for your attention.
Thank you, Rolf, very much for your presentation. Let us open the question and answer and discussion part of the seminar. Hopefully there will be some questions from the audience. Please switch on your mic and ask questions. If you like, ask any.
I don't have
okay.
Okay. I don't have a question, but sorry for interrupting. I don't have a question, but I just want to know. I mean, there are probably some references at the end of the slides, right?
Yes, we have some papers which are maybe somehow here distributed. So do you have particular? I can send you, or
so maybe I think it might be a good idea that you will provide me with some references that you feel are relevant here, and I will put this on our website as some additional material.
Okay, yeah, this I can do.
Below your abstract.
Mm-hmm.
Okay, we can do this offline.
Thank you very much.
Vasilis, I saw that you raised a hand, so if you want, you can continue.
Yes, thank you, Jakub, and thank you very much, Rolf, for the presentation. I do have one question. Actually, that's a really nice slide that you have there for my question, I think. So you are saying, like, for the parallelization, that you do that in the network level. Is that correct? Like, you assign different parts of the network to different, I don't know, cores?
Yeah, that's also what we do. I mean, this is, yeah. That's a third variant I didn't talk about, but exactly that's what we do, yeah.
Okay, and I'm trying to understand that, because that's like a serial process. Like the second box here requires information from the first box, and the third box requires information from the first and the second. In order to
for this,
do the
you're right. For this particular case, so what you can see here, of course, in order to evaluate the gradient, you need to go through the whole network, and this is what we do. Yeah, so your argument is right. It's just we change only the weights in this subset.
Okay, so for each core, you change only the weights corresponding to one part of the network.
Exactly.
Okay, how do you combine then all the different information for all the different cores to one network?
This is somehow key in a certain sense, and this is here. Okay, so what do? You do your local minimization steps and you get your local updates. This gives rise to local corrections. Okay, so differences between old and new values you have here. Okay, so those you can, I mean, you sum up, which means basically you put them into the original network and you make a update of your global weights. Then what you do at this point, after adding the updates from your cores, you evaluate the gradient and you do a step of BFGS with an approximate inverse, which you have here. And once you have done this, we do a momentum step. This is done here.
Okay.
And so you go ahead. And then the question is, how do you compute this approximate inverse? And this is some variant of BFGS. So, and this is very important. We call this nonlinear post-smoothing. So you have your local information. If you maybe know, there's a nonlinear domain decomposition method, which is called SPIN. It does a similar thing. You have your local corrections. You're just adding them to your global problem. And then you do an approximate Newton step on the global problem. And this synchronizes between these subdomains.
Okay. Okay. I see.
And
Okay.
there's a second answer when we do it completely separated. And this is when you go to, where do we have it? Yeah, when you go to nonlinear domain decomposition methods. Here we are. You need to construct, this is multi-level, but it also holds for the parallel term. If you look at a subproblem which has only information on parts of the weights on one core only, yeah, you only see parts of the weights. Then you would like to construct an objective which is only living in these local weights, yeah, because this was your original question. You said, okay, it might be I look only at part of the weights, but in order to evaluate my gradient, I need the whole network.
Yeah, yeah.
And what, right? This is somehow, and then you say, well, then it's not parallel, it stays sequential somehow. Yeah, and this is true. And so what you have to do, and this is what we do in parallel minimization, we construct a local objective, which is living only in the degrees of freedom you have available on your processor. This you can do. And how do you do this? By choosing any local objective you wish. Could be, for example, your loss function locally. You choose any local objective and then you add a first order correction term. This is quite standard in optimization. And how does it look like? You take the restriction of your global gradient. Yeah, this is your fine model, your global model. You compute the gradient using the whole network. You select the degrees of freedom of the gradient living on your single core. And from this, you subtract the gradient of the model you have been chosen locally. And what does it do? It simply says, if you look at the gradient of your new model, which consists of your chosen model and this first order correction, if you compute the gradient of this model, you see that the gradient of this one and this term here cancels. So the gradient of your low cost model, this first order consistent model, is nothing else than the restricted gradient of the fine level model, which means that by this modification locally without looking at global information, your first iteration step will always go in direction of a negative gradient of the fine model.
Okay, I
Maybe
see.
that's a little bit difficult to understand, but
I mean, if you share the slides, if they're available, it would be nice to
it's not difficult.
Later. Yeah.
So you construct a local model which in the first iteration steps can be seen to guarantee a decent property for the global model.
Okay.
If you do more steps, you lose this property. And then you hope for the best.
Okay. Okay. So I do have two relevant questions. First one is, can you comment on the memory requirements of, well, does it have better, does it require less memory compared to doing it all at once, like the method that you're suggesting without parallelization?
Does it? I mean, there is, of course, a certain overhead. But I mean, of course, you use less local memory. So what you can do is when you parallelize, you simply can sum up the local memory. So I do not need a single memory which is going to store the whole network.
Okay, but you have not tested, you do not have any diagrams or data to...
No,
Okay.
because this is something on the implementation of this we are working. And interestingly, our very first step needed was to write a new data loader, because what you get in PyTorch, anyhow, it was not suitable for parallel computing. So
Yeah.
because they always open and close files, and this is somehow going to kill you in this parallel environment.
Yeah. Yeah. And lastly, then, how does the method that you're suggesting compare with, instead having the parallelization on the network level, having it on the data level? Just split your data in different cores.
This you can also do, but if you split just on the data level, you get, I believe, it doesn't work so well. This is here. This is APTS in weights, and we did APTS in data, and APTS in data. So if you split in the data level, doesn't work so well as splitting on the weight level.
Okay.
Yeah, so this is, let me have a look. Yeah, because in the very end, what is happening, if you assign a certain subset of your data to a certain core, yeah, you're just looking at the information in this data subset. So somehow your accuracy goes down.
Well, but then you average to update all of the weights, or not necessarily average, you do something. I'm not an expert, but there should be a technique to gather all the local networks to one network.
Yeah, but
Basically.
that's not the point. The point is if you distribute in data, your local network will only see a certain subset of the data, and that turned out to be not as powerful as distributing the weights.
Okay, I see.
I mean, maybe you can save it somehow. Some trick. In our experiments, at least the approach we did, it didn't work so well.
Sure. Okay. Thank you very much for your answers and the presentation. And if you could share somehow the slides, that would be really nice. Thank you.
Okay, right. Are there any more questions in the audience? I can have one maybe from my side using that opportunity. So you showed some examples with the pins, right? The first example that you showed was the pin, which I believe it included the gradient in the expressions, I mean, in the weak form. Correct me if I'm wrong.
You mean we have, here we are. You mean for the PDE?
Right.
Okay, we have three. So this is because we are looking at something hyperbolic.
Right. So
we are looking at something. Yeah. So yeah, where you have strong advection, and we are looking at basically strong advection, but but stationary. Yeah. So elliptic and strong convection, some kind of heat equation with advection and hyperbolic.
Because this is the approach that you chose was the pin, right? The pure pin, in which you don't have a data component. You compute things on the fly, and you have the residual as a part of your loss function.
Exactly.
To get together with some boundary conditions. Terms. So, but in your residual, you have the gradient with respect to some coordinates, right? The spatial gradients or time gradients, meaning the gradient with respect to the inputs to your neural network. So, and now the question is, how do you evaluate those gradients in your approach?
You should use AD, yeah.
But then the second question that naturally arises is how do you choose your activation functions in your architecture? If you use ReLU, it is basically either 0 or a linear function. And after computing the gradient with respect to some input, it will give you a constant function in that direction. So that, and then it came to my mind after you started to talk about optimization of your, or finding the fitting of your neural network, or training your neural network, that you are using some quasi second order methods like LBFGS. I know that these are gradients with respect to the weights, not the inputs.
Exactly, yeah.
But still, I'm wondering whether there is any kind of bad connection between the fact that there is a constant dependency on the inputs and at this of some gradients, right? And at the same time, you have some sort of a notion of the approximation of the second order in your LBFGS. It is a very rough intuition, but it might be completely wrong. But perhaps there is something going on here. But maybe this is something
from what I understand.
irrelevant.
No, I think this is somehow one of the central aspects, because one is the smoothness of your approximating function, and the second one is the smoothness of your parameterization.
Right.
Right. So this is what you say, and what I believe is really key. One is the mapping from weights to approximating function, and the other one is input output. So what we usually consider to be the network.
Right.
And what you now say is, okay, if somehow my input output relation for training a PDE, or if my network gives rise to approximation of a certain smoothness, piecewise linear, how does it influence the training of the mapping? I mean, the training of the of the weights. So how is it connected to the smoothness of the
Right.
mapping from weights to approximating function?
Probably
I
not.
do not know, but I agree. I believe it's very important.
All right. So, yeah, I have several small questions and comments, but they are not that relevant to the main core of your presentation. These were rather observation towards the introduction, that very nice introduction that you have provided in the beginning. But maybe just one question, because this is something that drew my attention. That when you mentioned that the scaling with the necessary data to somehow provide the proper training to your neural network scales exponentially with the dimension of the input, which is something natural to think about. But also you mentioned that it scales exponentially with respect to the depth of the neural network.
Yeah,
and
that's what
this is what I was not thinking about before, and I would like to hear your thoughts on that in some more detail, if possible.
Why? Okay. I mean, I could say this is
Why in depth?
bellissima domanda. I mean, they provide lower bounds in this paper, so they claim somehow the estimates are sharp. I do not know. It seems to me, okay, but this is really a rough guess. Yeah, don't cite me. But it seems to me that the high expressivity of neural networks is very intimately connected to the fact that there's a hierarchical structure in their design, right? Because you have this concatenation of basically always the same thing, yeah, some linear whatsoever plus activation function. So you have a composition of functions. Yeah, you have this compositional structure of networks. And if you look at classical approximation error results, those compositional structures gives rise to possibly very strong approximation results. There is a little bit frightening result that with a network of, I believe, like 28 or 29 parameters and 4 or 5 layers in 1D unit interval, you can approximate any continuous function up to a certain error. And this to me means that if you have this, how can I say, hierarchical structure, then you get extremely strong expressivity of your network, which for me also means if you have this expressivity, you need the corresponding interpolation conditions. So I would interpret that by adding more layers, the network has the potential to approximate so well that you need to control it. And this can only be done by sufficient amount of data.
Okay, I see your point.
Yeah, that would be my argument.
Yes.
But as I said, that's
still,
my
I
guess.
need to think more about it.
Yeah, if you find a better argument, please let me know.
Okay, thank you very much for your explanation. So I don't know, I cannot see any request for asking a question. So let me conclude the seminar today. And thank you again for your presentation and to all the audience for their participation. And I will keep you updated about the future seminars. Have a good day today.
Thank you very much.
Thank you.
Bye.
Bye.